Yeah, thank you. I hope you can hear me well. Today
Yes.
we are going to try to answer the question whether the prompt engineering is. Oh, sorry, you wanted to say something.
So sorry. Iryna and Oleg are data scientists and co-founders of Dataforce Solutions. That is a company specialized in delivering end-to-end data science and AI services. Today, they are talking about how can prompts be automatically learned from data. And I remember you that at the end of the session, we are going to have a Q&A session. So please remember to use Slido to send your question to the speakers. So thank you very much.
Yes, thanks again. As I already said, today we are going to try to answer the question whether the prompt engineering is dead. Before we begin, you can scan this QR code to follow the slides on your screen. This probably would be a good idea because the screen is positioned rather low and some of the content might be obscured by me. Okay, so let's start with a bit of motivation. Why do we even care about prompt engineering? I guess it was really, really difficult not to notice that in the last couple of years, LMs were a rather big deal. For example, just looking at the NeuroIPS 2024 poster presentations grouped by topics, we can see that LMs take up a substantial portion. However, obviously, LLMs are not only popular amongst researchers, and we get more and more exciting tools like LangChain, Cursor, Copilot, etc. And even large enterprises are stepping in with their LLM-powered offerings. You probably know or used Apple Intelligence, which provides native AI capabilities to iPhones and Macs. However, when we look at how those systems are working under the hood, we see something like this. Very long manually crafted prompts with directives like, please do not hallucinate, please output your answer in a certain way, etc., etc. The overall idea is that complex systems require complex prompts, and crafting those prompts manually is far from being trivial. They need to be precise, non-ambiguous, and well-structured. Therefore, we can raise a natural question. Can prompts be automatically optimized given some training data? And basically, the answer is yes. And now I will hand it over to Iryna, who will explain how this can be done in practice.
Thank you. Before we proceed further, we need to make a distinction between simple or single component and compound or multi-component systems. In single component systems, we typically deal with just one prompt. Think of a summarizer or a translator. There is one input, one output, and the prompt is pretty straightforward. Tuning that prompt manually is actually a manageable task. You write the initial prompt, test it, tweak a word or two, and can already see satisfactory results. In contrast to simple systems, compound systems are made up of multiple components chained together in a pipeline. As an arbitrary example, imagine a retrieval augmented QA system. Here, our program first retrieves some documents, generates an answer that is grounded with these extracted text passages, summarizes, and then rewrites the text. Such multi-component systems are becoming increasingly more popular, and there are a few key reasons for that. First of all, they often outperform monolithic models, especially when designed thoughtfully. In addition, because each module is isolated, you can inspect each step independently. Also, you know that different tasks don't always require the same horsepower. With compound systems, you can use different LLMs for different tasks. For example, a smaller and cheaper model for extraction, while a more capable one for reasoning tasks. That lets us optimize cost-performance trade-offs more intelligently. Finally, such systems give you more ways to ground the model's output with external tools or some specific trusted data sources. But here's the catch. This added structure comes at a cost. We're no longer dealing with just one model or one prompt. Instead, we have a chain or graph of components, each with its own role and, more importantly, its own prompt. These prompts are no longer independent. For example, a change in the first component might alter the output a bit. That would result in a huge and unintended side effects in the later steps of a pipeline. Because of these cross-prompt dependencies, manual prompt optimization becomes infeasible. So while compound systems offer important benefits, they also introduce serious challenges in terms of prompt optimization. We already established earlier that there must be a way to approach prompt optimization like a machine learning task, where we treat the prompt itself almost like a trainable parameter and optimize it based on some training data. But how can we do that? It turns out that the simplest technique we can apply is called few-shot in context learning. The idea is very simple. We just put several labeled examples directly into the prompt. For instance, to improve text classification, we can supply several text label pairs directly in the prompt alongside a very generic instruction. That way, we obtained a much better prompt without much of handcrafting. However, here we have a single component system. Applying the same technique in a compound system is not that straightforward. Why is it the case? Because in multi-step pipeline, we usually only have access to the initial input to this pipeline and the final output that's produced by a pipeline. But we don't have any intermediate input-output pairs between the modules. However, we can use the training data and a teacher model to construct, trace, and save the intermediate results that would be used at a later point as few-shot demonstrations. This approach is used by a technique called bootstrapped few-shot. The idea is as follows. First, we run training input through our program. If the output is a highly scoring prediction as assessed by a specific metric, then we keep this trace. Otherwise, this trace is discarded. This process repeats until the maximum number of good or high-performing examples is collected. Before we proceed with other methods, let us zoom in into one important component of this process, the metric. The metric is what tells us whether a model's output is good enough to be saved as a demonstration. In simple cases, we can use traditional metrics such as F1 score, accuracy, etc. But most real-world applications don't produce simple outputs. They usually generate long-form text, such as summaries, explanations, translations, and so on. For these cases, we can use another language model to critique or score the outputs based on some desired qualities. For example, correctness or some domain-specific requirements like adherence to a brand voice. Let's now look at another method for prompt after optimization, which is called bootstrap few-shot with random search. It's based on the idea of bootstrap few-shot, but it takes it one step further by searching for the best performing combinations of demonstrations. Let's go through how it works. First, we generate a set of good input-output traces. Then, instead of just inserting these traces into the prompt, we randomly sample different subsets of these traces. Next, each sampled combination is evaluated, and finally, we select the demonstration that leads to the highest validation performance. You might have noticed that so far the primary approach for prompt optimization was simply adding labeled demonstrations directly into the prompt without doing anything with the instruction. And it turns out that this method is quite powerful. In fact, some studies show that optimizing just the demonstrations can lead to better performance than optimizing the instruction alone. However, the instructions become more popular, more important in tasks with complex conditional logic. Moreover, joint optimization of instructions and demonstrations generally yield the best results. So how can we achieve that? One of the most well-known methods is called multi-prompt instruction proposal optimizer, or MIPRO. It is able to optimize both instructions and demonstrations at the same time. First, we collect high-scoring input-output traces. Then, to propose instructions, MIPRO doesn't just rely on language model's internal knowledge, but it grounds it with some meaningful context. For example, summary of the dataset, overview how the pipeline flows from module to module, bootstrap demonstrations, and historical information about prompts and their evaluation scores. Finally, the best combination of instructions and demonstrations is found using Bayesian optimization strategy. This is a powerful method because it allows to explore a huge space of instructions and demonstrations and pick a combination that works best together. However, MIPRO might still be limited in one key way. It uses a single feedback signal to optimize all modules. That makes it difficult to improve prompts precisely. The optimizer doesn't know which module is responsible for a poor performance. Making an analogy with a deep learning, it's like training a neural network without gradients. You just try different things and see what sticks. The concept that might solve this problem is textual gradients. Just like in neural networks, we could backpropagate those gradients to quantify how each parameter contributes to overall loss and provide direction for optimization. Protege mimics this idea by using natural language explanations of what went wrong as textual gradients. It starts by running the initial prompt on a mini batch of data. Then it uses the first prompt template that instructs the language model to describe problems which could have led to these mistakes. This response is our semantic gradient. It points in the direction of what is wrong. Then the second language model takes that feedback and edits the initial original prompt to correct those mistakes. This loop continues recursively and the most highly performing prompt is selected. TextGrad builds on the core idea of Protege, but it allows for systems of arbitrary depths and multiple trainable variables per prompt. According to some benchmarks, TextGrad can be on par or even better than Bootstrap few-shot with 8 demonstrations. Now that we covered some essential theory, I would like to hand it over back to Oleg, who will walk you through available prompt optimization frameworks and more practical code examples.
Yes, so when it comes to prompt optimization frameworks, without any doubts, the most popular one is DSPy by Stanford NLP. As their own motto says, it's used for programming, not prompting language models. And indeed, in DSPy, prompts are completely abstracted away from the users through a concept known as a signature. A simple signature might look just like this, which is just a string, and by looking at this string, we can intuitively understand that we want to have a question as an input and an answer to this question as an output. In addition to that, we want our answer to be a floating point number. To test that it works, we can create a very simple DSPy program, First, we initialize a predict module with our signature, and we will talk about modules a little bit later. And then we call our module with the question, what is an average weight of a cat? And here we received 4.5 as an output, which is a floating point number. So it seems to be working. However, such simple string-based signatures might not be sufficient for more complex problems. For example, what if the variable names within our signature are not self-explanatory, or we want to provide an additional initial instruction to the model? But luckily, this can easily be done in DSPy using the class-based signatures. For example, here we have a more complex signature where we want to check the faithfulness of the text given some factual context. The model should produce its answer and also a list of supporting evidence. In such signature, we provide an instruction as a docstring and the specifications of input and outputs as attributes. As you can see, the fields in the attributes can also be provided with optional descriptions. So how do we use such class-based signatures? Actually, we use them the same way as the string-based signatures by passing to the modules. And actually, under the hood, all signatures are being converted to signature objects anyway. But you might be wondering how or where those signatures are actually used. And to answer this question, we can actually check the raw messages that are being passed to the LLM. And here we can see that our signature got automatically converted into a rather long system message. It starts with the specifications of the input and output fields, then the description of the expected format, and finally the instruction itself in the bottom. So now that we more or less understand how signatures work, we can talk a little bit more about modules. In DSPy, modules are basic building blocks. And if you are familiar with PyTorch or some other similar deep learning framework, you would find a lot of similarities. DSPy supplies several pre-built modules. However, today we don't have enough time to go through all of them, but let's just check two. We are already somewhat familiar with the predict module, which is the simplest one. It just takes the signature and executes it without any modifications. An example of a slightly more complex module would be a chain of thought module that modifies our signature by adding an additional reasoning output field. This way, the model would always be forced to produce its reasoning before the final answer. And exactly like in PyTorch, we can create our own modules. For example, here we built a simple chain that first translates and then summarizes the text. The final two components we need in order to optimize our module are teleprompters and metrics. Again, drawing an analogy with the PyTorch, a teleprompter would more or less correspond to an optimizer, which iteratively adjusts the instructions and demonstration within each submodule of our module that we are optimizing. And once we have a module that we want to optimize and the teleprompter initialized with a metric, we simply call the compile method, which is an equivalent of train or fit. So to sum up, in DSPy, you would usually create custom modules using the built-in ones as the main building blocks, and also the signatures as abstractions over the prompt templates. The custom module would then be optimized by a teleprompter based on some supplied metric. And now let's take a look at another framework called TextGrad, which is also the official reference implementation of the TextGrad method presented earlier. Unlike DSPy, TextGrad is actually rather low level and small and provides only a handful of blocks out of the box. First important concept that we need to know in TextGrad is a variable. A variable can be a full or partial prompt, then can be optionally optimized by setting the respective value of the requires read. To use these variables, TextGrad provides a built-in black box LLM module that takes one variable in init for the system message and another one in the call for the user message. Now, in order to optimize our variables, we use the same syntax as we would in PyTorch. First, we initialize the optimizer, then we initialize the loss, then we calculate the loss, and in this case, the loss is just an output of a judge LLM. Then we call backward on the loss and step on the optimizer. So exactly the same thing as in PyTorch. And actually, this is more or less everything that you need to know about TextGrad. It's really simple and intuitive, but at the same time, some things cannot be easily implemented out of the box. For example, what if we wanted to optimize on the specific part of our prompt and hardcode the other one, or provide a few short demonstrations as in DSPy. And this brings us to the last framework for today called AdalFlow. Overall, it can be viewed as an extension of TextGrad, but with some things taken from DSPy. Given that we don't have that much time left, we will only go through some of the most notable differences between TextGrad and AdalFlow. So in TextGrad, we had variables, and in AdalFlow, we have parameters. But now we have two different types of parameters: prompts to hold textual instructions and demos to hold future demonstrations. These parameters can be used in the explicit prompt templates. Hence, the prompt template can have both a static hard-coded part and a dynamic optimizable one. The functionality related to a certain pipeline can be encapsulated in a component, which is more or less exactly the same thing as a module. But finally, to optimize our component, we first need to wrap it into another Adal component, which is a special type of component that expects the component we want to optimize, the loss function, and the evaluation function. Finally, when we have our Adal component, we can pass it into the trainer and call fit on the trainer. This might look a bit too verbose, but at the same time, it's actually not that different from what we've seen with other frameworks. So to sum up, AdalFlow is a very feature-rich framework that combines the ideas of TextGrad and automatic few-shot learning like in DSPy. But in my opinion, it might be a bit too verbose, as we saw, which is not necessarily a bad thing, but at the same time, it might potentially imply a steeper learning curve. And finally, let's get back to the original question: is manual prompting dead? And as always, the answer is not that obvious. Without any doubts, automatic prompt optimization is a viable technique. It is fast, simple, and in most of the cases, still cheaper than manual effort. However, there are still some potential limitations. First of all, the underlying optimization technique is still based on the manually crafted meta prompts. And those meta prompts are not necessarily well optimized for your specific problem. In addition to that, by using the automatic prompt optimization, you are bound by the reasoning power of the LLM, which can be limited. Therefore, it might be a bit too early to declare the death of manual prompting for now. Yet, automatic prompting is a viable alternative, and we definitely encourage you to try it on your specific problem. And if you want to try it, but you don't really want to learn a new coding framework for that, at Dataforce, we have recently launched an open beta of our ML Studio, which also includes a no-code prompt optimization module. It is live, 100% free, and to be open sourced within the next weeks. So you can access it using this QR code, and we would really appreciate it if you try it out and provide your feedback. And from our side, that's it, and we are ready to answer your questions. Thank you.
Thank you very much. So we have time for some questions for you. So do you think some models respond better than to the others to the previously presented prompted approaches? So can you rate some?
Yes. So basically, a general idea is that those prompt optimization approaches are based on meta prompts, as I said, and therefore the model that follows the instructions the best would be the best model to try for these things. And generally, those are the models from OpenAI, Claude, and so on. So the major closed source models.
Okay. And are DSPy signatures a kind of function calling?
No, not really. It has nothing to do with the function calling. Actually, basically, if you look at the, okay, maybe here, when you have a signature, in the end, it gets transformed into a system message that just describes what inputs the model should receive and what outputs it should produce and in which format.
Okay. What about an approach to prompt optimization based on genetic algorithms?
I mean, it could be done. I'm pretty sure. I'm not really familiar with the. I don't think that genetic programming is implemented into any of the big frameworks. But at the same time, Bayesian optimization is. I mean, it's kind of different, but the idea is the same. You just generate lots of instructions and try to figure out which one are the best.
Okay. And could you share a practical task or use case where you would manually optimize the prompts and then move instead to the automated ones?
Yeah, so basically I would say that the simplest task and also the most prominent in this case is classification, because here it's really, really easy to come up with a metric. You can just use the exact matching, and it's a well-defined task. Obviously, when you have some tasks that require more creativity, you can still use the automatic prompt optimization because you can use the LLM as a judge. However, it might be more subjective. Therefore, if you have a task with a strictly defined correct answer, then prompt optimization should be much, much better than the manual optimization.
Just because you shared something about the LLM as a judge now, somebody asks if we can use prompt optimization techniques with limited training data, perhaps using an LLM as a judge.
Yes, so basically you can use prompt optimization without data at all. You could even generate the data, so probably the answer is yes.
Probably. And can you expand a bit on TextGrad methodology? So how it is text modified to obtain a new text version after computing the gradients?
Okay, so in this...
That's a tough one.
I mean, it's not really a difficult question, but at the same time, I'm not sure that we have enough time to go into the details. But overall, the idea is that you get the natural gradient, and the natural gradient is basically a description from another LM what was wrong with the output of the current module. And then we pass this feedback and our current instruction to another LM and say, okay, so we had this instruction, we had this output, but according to another LM, what was wrong with this output, so can you now modify the instruction so we don't have this problem in the output? And we repeat it continuously. Okay.
And last curiosity for our audience, which of the presented libraries do you use the most in your daily job? So what's your favorite one and why?
My favorite one is Dataform Studio.
Surely.
Yeah. But overall, DSPy is way more popular than TextGrad and AdalFlow. So TextGrad, as I said, is just a very, very small library. I'm not really sure that it's that convenient to use it in production. AdalFlow is very promising, but at the same time, it's only an emerging thing, and we will see how it turns out in a couple of months or years.
Okay, so thank you very much, Oleh. Thank you very much, Iryna.
Thank you.